take a look at the trends in the periodic table, please read the OER textbook chapter 4.4. After you finish watching this video, please start working on homework 4.4 as soon as possible. So this is the trend that we are going to take a look at. We are going to take a look at the size of an atom or atomic radii. We're going to look at the electronegativity, the trend in ionic radii, the trend in the energy that associated with ionization, and the trend in the electron affinity, and the last one is the trend in metallic character. Okay. So what I'm going to do is I'm going to start with three elements that we are going to compare, and these three elements will help us to determine the size of the rest of the main group element on the periodic table. What should be the trend when we talk about the size. Okay, so when we talk about the size of atom, we are going to look at the atomic radius. Okay, so we are going to measure from the nucleus to the outer shell valence electron. Okay, so in this case, I'm just going to go ahead look at the periodic table of the location of these three elements first. So what we have is we have lithium, sodium, and phosphorus. So if I write out the electron configuration of lithium, it would be 1s2, 2s1, right? So therefore, in this case, you notice that there would be two shells that associate with this. Okay, so there will be two shells that associate with this. If I do the same thing with sodium, you are going to start with 1s2, 2s, 2p6, and then 3s1. So therefore, in this case, for sodium, there will be three layers that associate with this, right? So there will be three layers because the number that come before the letter indicate the main energy shell. Okay, so if I do the same thing for phosphorus, okay, if I do the same thing for phosphorus, what you are going to get is going to be 1s2, 2s2, 2p6, 3s2, 3p3, right? So in this case, there are also three energy shell as well. Okay, so 1, 2, and then the third one right here, right? So this is n equal to 1, right? This is n equal to 2. Same thing for this is n equal to 1, n equal to 2, and then this one is n equal to 3. Same thing for phosphorus as well. We have three main energy level, n1, n2, and n3. But each of these energy level will have different number of electron resides in each of those energy levels. So I'm going to use this quantum mechanic model, which is express the location of electron in an atom, and use a simpler model, which is the Bohr's model, to help us understand this. I'm going to use this electron configuration in order to draw the structure of an atom for lithium. Okay, so that means in this case for lithium, lithium would be Li, right? This is the nucleus of it. Okay, so I'm going to draw the nucleus. Actually, let me do this in the middle. Okay, so we have lithium. Okay, and lithium, if I go back, okay, so lithium has 3 protons. So I'm going to do 3 proton in here. Okay, so and also it include neutron as well. Okay, so we don't have to worry much about how many neutron in here. Okay, so we are going to take a look at the number of proton. Okay, so I'm going to actually make sure that this is a little bit clearer. So this is nucleus contain +3. Okay, so +3 coming from the charge of the proton. And if you go back from the previous slide that I say here, is you will see that there are 2 shells, right? So that means in this case, I can draw the 2 energy levels. So n equal to 1. Okay, so this is n equal to 1. This is going to have, if you go back, 2 electrons, right? So these are the number of electrons right here. Okay, so in this case, if you go back here, there will be 2 electrons. Okay, so I'm going to draw 2 electrons. Okay, 1, 2. Now if you go back again, the second shell, okay, so that second shell contains 1 electron. Okay, the subshell that is reside in this is 2s, right? So we don't actually have to worry about that. We can combine them. Okay, so in this case, I'm going to draw another one right here, and this will represent n equal to 2, and there are how many electrons here? So there are, right here, 1 electron. Okay, so this is number of electron. Therefore, the second energy level would have only 1 electron. So I'm going to draw right here. Okay, so before I move on to the next element, what I would like you to look at is, I would like you to look at how electron experience the charge of the nucleus. Okay, so if you remember from previous video when we talked about shielding effect, how the s orbital can penetrate, get closer to the nucleus than the p orbital. I talked about this shielding effect before. Okay, so shielding effect is when the inner electron is blocking the charge from the nucleus away from the outer electron. So that means the outer electron would experience less charge than the inner electron. So that's what the shielding effect is. Right? So similar to when you go to the concert, right? If you are further away, you are not going to be able to see the artist very well, right? So because the people in front of you shielding that, right? Because you are not able to see that. Okay, so what we are going to, how can we quantify how much the outer electron is actually experiencing the nucleus? Then we can quantify that by using the effective nuclear charge. Okay, so CFF, this is effective nuclear charge. Oops, sorry. Effective nuclear charge. Effective nuclear charge is the actual charge that electron experience. Okay, so this tell us about the actual. Oops, sorry. I'm gonna abbreviate this. So electron experience. Okay, what do I mean by that? Okay, so for example, the interaction we are looking at is the interaction between the negative and the positive, right? It's the attractive force or the attractive interaction between the nucleus and the electron. Okay, if you're looking at the proton, okay, so inside the lithium nucleus, you see that there are 3 protons. So therefore, the charge of the nucleus would be positive 3. The charge of each electron would be positive 1. These 2 electrons, because there is nothing inside of these blocking their view of seeing the nucleus, therefore, how these 2 electrons experience the nucleus would be equal to the charge of the nucleus. That means in this case, in order to calculate for effective nuclear charge, okay, the effective nuclear charge can be calculated by using the number of protons inside the nucleus minus the number of shielding electrons. Okay, so that's how you can calculate for it. What do we mean by that? Okay, so if I looking at how this electron right here experience the nucleus charge, you can calculate the effective nuclear charge by equal to the number of protons. How many? Well, 3, right? How many shielding electrons? There are 0 because there's nothing shielding it inside this layer. Therefore, in this case, it would be 3 minus 0. Therefore, the effective nuclear charge that this electron experience would equal to 3. Okay, or 3 plus, right? Now, if you consider a different electron, right? So if you consider this electron, it would experience the same, right? Because these 2 are not blocking their own view because they are in the same layer. They're not blocking each other. Okay, so this one also going to experience effective nuclear charge equal to 3 as well, according to this, right? So it's 3 from the proton minus number of shielding, which is 0. So it's going to experience effective nuclear charge equal to 3 as well. The higher number of effective nuclear charge, it indicates that it's a stronger interaction. Okay, so now what about the outer one? Okay, so what about this one? If you calculate effective nuclear charge here, this electron would experience how much? That's what we're going to take a look at, right? So we're going to use the number of proton, okay, so which is 3, okay, minus the number of shielding electron. Okay, so this is the outer layer. How many electron in the inner layer? So that would be the shielding electron. The number of electron in the inner layer would be the number of shielding electrons. So in this case would be 1 and 2, right? Because these 2 are blocking the view of this. Because remember, they're not staying as static, right? They're moving around as dynamic. They're moving around all the time. Therefore, these 2 are going to blocking the view of this electron. Is going to shield the charge from the nucleus away from this electron. Therefore, in this case, we are going to do number of proton minus the shielding electron, which is 2. So that means in this case, Okay, the total of the effective nuclear charge that the outer electron would experience for this lithium would be 1. So again, the higher the number of effective nuclear charge, okay, so effective nuclear charge, the higher the number or the higher the value tell us that the electron experience a stronger, it indicates stronger attractive force. Between the electron and the nucleus. Okay, so that means in this case, if you compare between these two electrons versus the outer electron, you will see that the outer electron experience less attractive force compared to the inner electron because it's closer, right? It's going to experience a stronger attractive force than the one that is further away. Okay, so why are we going to talk about this? So this is going to be important in terms of analysis of the size of an atom. Okay, so pretty much if the stronger the attractive force mean that it's going to be able to pull up electron closer to itself, right? So if the effective nuclear charge is strong, it's going to be able to pull electron closer to itself, therefore the size would be smaller, right? So that's why we are going to take a look at in the next. But right now, what we see so far is just the lithium. Okay, so we are going to take a look at sodium and phosphorus as well. Okay, so let's take a look at sodium and phosphorus. So for sodium, we already see, right? So if I go back here, sodium contains 3 layers. Okay, so the first layer contains 2 electrons. Second layer contains 8 electrons because you need to add these 2 together. These 2 are the subshells that reside in the main energy level 2. This is 1 electron. This is the subshell that reside in the main energy level 3. Okay, so that means in this case, what I'm going to do is, okay, so I'm going to draw sodium. Okay, so I'm going to draw sodium. And what is the number of proton? Well, it's 11. Okay, so I'm going to do plus 11. Okay, so again, the plus 11 come from the positive charge of the proton that resides in the nucleus. Why don't I talk about neutron? Well, because neutron has 0 charge, right? So in this case, I'm going to talk about only the proton positive 11. Okay, so we already analyzed that the first layer of sodium contain 2 electrons. Okay, so I'm going to do 1, 2. Okay, the second layer contain 8 electrons. So I'm going to do second layer with 8 electrons. So let me use different color. So it's 1, 2, 3, 4, 5, 6, 7. Do 8 here. 8. Right, so again, so how did I get 8? If you go back here, 8 come from 2 from the 2s and 6 from the 2p. These are in the same main energy level. Add together, you're going to get total of 8 electrons in the main energy level 2. Okay, so the third layer, okay, contain 2 electrons. Okay, so oops, my drawing is bad, so let me actually draw this better. Okay, so this layer contains 2 electrons, so it would be 1 and 2. Oh, actually, let's see. That might not be, let's see. I think it might be just 1. Since group 1. Yep, so sorry, it's only 1 electron, sorry. So shell number 3 contains only 1 electron. Okay, so in this case, yep, so I'm going to just include 1 electron here. All right, we are going to do the same thing. What I would like you to do is that I would like you to calculate the effective nuclear charge for each of these electrons. So it's for this one, okay. Again, the electron in the same layer would experience the same effective nuclear charge. Okay, so because the distance from the nucleus and how it's blocking the view would rely on only the inner shell. Okay, so in this case, these 2 would experience the same. So you just have to calculate 1. Okay, so the second one that I would like you to calculate would be this one right here. Okay, so tell me what is the effective nuclear charge of this. Okay, so and also this one as well. And the last one would be the valence electron, which is this electron right here. Okay, so I want you to look at the effective nuclear charge of this. Okay, so let's pause the video now and calculate effective nuclear charge of those electrons in a different energy level, and then check your answer with me. All right, let's take a look at the first one. Okay, so effective nuclear charge of the first electron, how many is going to experience? You are going to look at the number of protons. So there are 11 proton. Okay, so 11 minus shielding electron. This electron right here, is there any inner layer electron that's shielding it? The answer is no, right? Because this is the nearest. There is nothing shielding it. There is no other electron inside of this, right? Because remember, according to Bohr's model, right, electron have to reside in specific energy level. So in this case, there's nothing else in here. Okay, so that means in this case, there is 0 shielding electron that shield this. Okay, so that would be 0. So therefore, effective nuclear charge of this would be positive 11. Wow, that's a lot, right? Now what about second electron, the second layer of electron? Okay, so again, all of this would experience the same effective nuclear charge. We have to just calculate for one here. So number of proton is 11 minus shielding electron. This layer, what is the inner layer inside this layer? Well, the answer is this layer right here, right? So in this case, you will see that there are 2, right? There are 2 shielding electron that shield this electron. Okay, so that means in this case, you are going to minus 2 because going to be number of proton minus number of shielding. Number of shielding electron come from the inner electron. Okay, so in this case, it's going to equal to 9. Okay, positive 9. So that means if you're looking at it, right, so this one would experience, this electron right here would experience less attractive force from the nucleus. This one would experience the strongest. Okay, so what about the last one? Okay, so the last one, you are going to do the same. Use number of proton 11 minus number of shielding electron. Okay, so how many shielding electron? Well, if you're looking at this, right, there are 2 more layers. There are 2 more layers here, right, that is shielding this electron. Therefore, what you are going to do is you are going to count all of the number of electrons that inside of this, right? So in this case, you are going to add 2 together with 8, right? Total would be 10. Okay, so this would be 10. So again, how did it get 10? Well, because the number of electrons that's shielding this electron are all the inner shells electron, which is 8 plus 2, that's equal to 10. Therefore, in this case, if you count this, you are going to get, you are going to get positive 1, which means that you probably noticed that for sodium, the outer shell electron experience the least of the attractive force from the nucleus. Therefore, it's going to be further away. It's going to be easier to be loose, right, or be gained in this shell because in this case, there is not a lot of attraction force to like keep the electron with it, right? So that's why you will most likely see group 1 most likely to lose 1 electron is because of that. Okay, so I'm going to let you do the same thing. Okay, so the next thing we're going to take a look at is the phosphorus. I want you to use the electron configuration that we used earlier. Okay, so this one right here. I want you to draw me the similar structure, which is the Bohr's electron shell model like this, but for phosphorus. Okay, so let's pause the video now and let's check your answer with me when you're done. All right, let's check your answer. Okay, so phosphorus, okay, contain 15 proton. Okay, so that would be 15 proton. And the first layer, so we have 3 layers. So I'm just going to go ahead and do 1 layer, 2 layer, and 3 layers. Okay, the first layer contain 2 electrons. Okay, 1, 2. Second layer contain 8. Okay, so 1, 2, 3, 4, 5, 6, 7. Oops, sorry. And then 8. Okay, the third layer contains 5, right? So it would be 1, 2, 3, 4, 5. All right. Now, let's calculate effective nuclear charge as well. Okay, so we're going to take a look at this one. If you're looking at this one, effective nuclear charge would be 15 come from the number of proton minus 0 because there is no shielding electron. Therefore, it equal to 15 effective nuclear charge. Second layer, okay, so if we consider this electron right here, effective nuclear charge of second layer would be 15 minus 2, right? Because the inner layer are 2. Okay. Total would be 13. Okay. The outer shell electron right here would be effective nuclear charge would be 15 minus, okay, minus shielding electron 2 plus 8, total would be 10. Okay, so therefore in this case it's going to experience plus 5 of the nuclear charge. Okay, so these are positive because it's the charge of the nucleus, right? So it would be positive. Okay, so here what we are going to do next is we're going to use this idea to help us determine the size of an atom. Okay, oops, sorry. Note that again, the effective nuclear charge that we are talking about is stem from the Coulomb's law, right? It's the what do you call it? It's the attractive force between the two opposite charge, right? So that means in this case, if these two are opposite, you are going to end up with the interaction with a negative energy or with the negative value of the force, right? It's indicated that they both are attract each other, right? Because if you multiply this, you are going to get the opposite charge, which is the opposite sign, right? But if you have the same charge, let's say positive and positive or negative, negative, you are going to get a positive sign of the energy or the force, and that's what going to indicate repulsion. Okay, so what we are going to do is that we are going to go back here. Okay, what we are going to look at, there are two things we're going to look at. Okay, so between lithium and sodium, clearly if you compare between lithium and sodium, okay, so lithium has only what? If we go back here, it has only 2 layers, right? So clearly lithium is going to be smaller than sodium and phosphorus, right? Because if you're looking at sodium and phosphorus, they have 3 layers, right? These also have 3 layers. But but lithium has only 2 energy level. So in this case, when you are looking at the an atom, right, the atomic size or atomic radius, which is going to determine from the distance from the nucleus to the outer shell of the electron, you will see that this one is going to be smaller atomic radius compared to sodium, where you are measuring from the nucleus to the outer layer of the third energy level here. So therefore, in this case, if you are comparing between sodium and lithium, clearly lithium is going to be smaller than sodium because of the number of energy level that we mentioned, right? So we have lithium, and you have only 2 energy level, versus if you're looking at sodium, right, you are going to end up with 3 energy level. Okay, so I don't actually have space for that. Okay, so we have, if we talk about sodium, okay, you are going to end up with a bigger size of the atom because contain more energy level. Okay, so when you compare top to bottom like this, you are going to use the number of energy level to tell us. Okay, so we are going to use the number of n, which is the number of energy level, to tell us about the size. If you're looking at how the electron outside of sodium and lithium is experienced, right? So we already calculate this electron in the outer shell, the effective nuclear charge of these two are equal to +1 according to what we calculated earlier. Right, this is equal to +1. Now, when you talk about the trend of the periodic table from left to right, okay, so I'm going to compare between sodium and phosphorus. Okay, so now if you're looking at phosphorus and sodium, okay, so let me write that. Okay, you will see that if you draw the energy level, there are 3 energy level also. That means in this case, between these two, you cannot use the number of shells to tell, right, whether which one is bigger or smaller. But what you can do is that if you're looking at the effective nuclear of the outer electron, okay, so electron in this location right here, okay, effective nuclear charge of this one, we just calculate that, right, for phosphorus is +5. You will see that if you compare between top to bottom, you can use the energy level. It's clear, right? This is smaller, this is bigger because contain 2 energy shells. This one contain 3. But if you're looking at phosphorus and sodium, this one contain 3 energy level. This one also contains 3 energy levels, so therefore you cannot easily tell by the number of shells, right? Electron shells. Therefore, the next thing you're going to look at is how the last electron or the outer electron experience the nucleus. Okay, so if you're looking at phosphorus, you will see that this electron experience positive charge from the nucleus. This electron here experience only +1 charge from the nucleus. Which one experience a stronger attractive force than the electron in the sodium or the electron in phosphorus? The answer is the electron in the phosphorus experience a stronger attractive force. Okay, what does that mean? Well, if it's experience stronger attractive force, that means that the nucleus would have ability to pull, right? Because pull or attract electron to get closer to itself. Therefore, in this case, the outer electron of the phosphorus would be closer to the nucleus than of the sodium, because the nuclear charge that this electron experience is much stronger. Therefore, the attractive force would be stronger. It's going to be able to get closer to the nucleus. Therefore, in this case, if you go from left to right, what you are going to use is you are going to use effective nuclear charge to compare. Okay, so the higher effective nuclear charge, the smaller the size of the atom. Okay, so in this case, if you compare between sodium and phosphorus, you are going to see that phosphorus would have a smaller atomic size compared to sodium. Okay, so of these, I already summarized this in this slide right here. If you want to like jot down what I just mentioned, right? So pretty much this is the summary of what I just explained earlier. If you go from top to bottom, right, on the periodic table, the electron shells increase, atomic radius will increase as well, right? If you move from left to right, you are going to have to use effective nuclear charge to help you determine, right? So move from left to right, you are actually increasing the number of proton, right? Because going from 11 to 15, the number of proton increase. And the number of shielding electrons are the same, right? So if you're looking at the number of shielding electrons between sodium and phosphorus, they are the same. But because moving from left to right, you are increasing the atomic number, but shielding electrons are the same. Therefore, the effective nuclear charge will increase moving from left to right. Therefore, the electron will experience a stronger attractive force from the nucleus. Okay, so the size of the atom will get smaller. Okay, so that's exactly what I mentioned earlier. So my expectation is that on the exam, you will need to not only predict which one is bigger or smaller, but you will also need to tell me as well why. Okay, so again, these are the two reasons. Okay, so one is using the number of electron shells from top to bottom. The other is using the effective nuclear charge, moving from left to right when they have the same number of energy levels. Okay. All right, so note that the reason sometimes when I grade exam, when I ask students to explain something, they do not give me the true explanation. For example, if I ask you why phosphorus is smaller than sodium, student will tell me that, oh, because moving from left to right, the atomic size gets smaller. That is not the reason. Okay, the reason is moving from left to right, the number of protons increase, but shielding electron is the same, right? The effective nuclear charge increase, electron experience attractive force stronger, therefore the size would decrease, right? So that's the true definition, or that's the true explanation that I'm looking for. Okay, so if you just tell me that moving from left to right, it gets smaller, you are not going to get any point, because that is not the reason. It's like me asking you why the sky is blue, and then you tell me because it's blue, right? It doesn't give me any explanation for that, right? All right, so what I would like you to do next is I would like you to look at example 1. Okay, we are going to compare between chlorine and iodide, and also magnesium and iodide as well. Okay, so here is the periodic table. Okay, so magnesium, so what is the first one? Chlorine and iodide. Okay, so chlorine is right here, iodine is right here. Okay, so same thing, this is in the same column, right? So this is n equal to 1. So that means this is the, oops, sorry, I don't have enough space there. So this is n equal to 1, right? This is n equal to 2. If you keep counting, chlorine would have 3 energy level, but iodide would have 5 energy level. Which one is bigger? Clearly it's going to be iodide, right? So that means in this case, iodide would have a larger atomic size than chlorine. The reason for that is because have more electron shares than chlorine. Okay, now let's take a look at magnesium and iodide. Okay, so magnesium is right here, iodide is right here. Oh, clearly also magnesium would have only n equal to 3, right? 3 energy level. And this one clearly is have 5 energy level. Therefore, in this case, clearly the size of the atom would determine by the number of energy level that located inside the electron. So therefore, in this case, it's going to be iodide that have a bigger size. Okay, but what if I go back here and I ask you, hey, what about if you compare between magnesium and chlorine? Which one would be bigger then? This one is when you cannot use the number of electron shells, because if you're looking at it, right, this one would contain 3 electron shells. This one also contains 3. So therefore, you cannot compare by using this, but you are going to compare by using effective nuclear charge. Right? So between these two, you're going to use effective nuclear charge. Which one has higher effective nuclear charge? Their electron would experience stronger attractive force. Therefore, the size will get smaller. Okay, so that's how you actually determine this. Okay. All right, so the second one that we are going to take a look at is, or what I expect you to be able to do is to be able to rank the atomic radii for several elements that I will give you. Okay, so for example, in this case would be phosphorus, fluorine, rubidium, and sodium. Okay, so let's see where they are. Okay, so we have phosphorus. Okay, what else? Oops, sorry. Fluorine, rubidium, sodium. Okay, so we have fluorine, and we have rubidium, and we have sodium. All right. So the first thing that you are going to look at is, remember what we are going to look at about the size. We are going to look at the number of electron shells, right? The number of principal quantum number. And if the number are the same, then what you're going to look at next is the effective nuclear charge. Okay, so that would be the step that you are going to take a look at. Fluorine. Okay, so if you're looking at the number of energy level, if you do electron configuration and draw it, you are going to see that fluorine will have 2 energy level. Okay, phosphorus would be n equal to 3. You are going to have 3 shells. Sodium would located n equal to 3. There would be 3 shells as well. And rubidium would be 5 shells. Will have 5 shells. Therefore, clearly in this case, which one is the smallest? It's going to be fluorine, right? So in this case, clearly what we have is fluorine would be the smallest. Okay, which one would be the biggest? Well, clearly rubidium has 5 layers. So therefore, in this case, rubidium would be the biggest. Okay, now between these two, okay, they both have the same energy level. Therefore, we cannot use the number of energy shells to compare these two. You are going to need to use effective nuclear charge. Okay, effective nuclear charge of the valence electron. Okay, so we are going to look at effective nuclear charge of the valence. Let me actually rewrite this. Okay, effective nuclear charge of the valence electron for sodium. We already calculate this, right? So if you go back from the previous slide, you will see that it's come from 11 minus 10. This is positive 1. This one is come from effective nuclear charge of the valence. Okay, so this is of the valence electron. This is of the valence electron. Is equal to 15 minus 10, which is equal to positive 5. You see clearly that electron in the phosphorus, which is the valence electron, is experiencing stronger attractive force. Therefore, the size of the phosphorus would be smaller than the size of the sodium. Therefore, the rank would go from fluorine would be smallest, followed by phosphorus, followed by sodium, and then rubidium would be the biggest. Okay, so that would be the order of that. Okay, so in this case, it's actually asking for rank in terms of decreasing. So that means what you need to do is you will need to flip that, right? Because we want to rank from decreasing, so you need to flip this. So that's why the actual correct answer would be going from the biggest one to the smallest one. Okay, so read the question carefully when you answer the problem, because it's going to so you don't make a mistake, right? So that way you get full point for that. Okay, so looking at whether asking for decreasing or increasing atomic size. Okay, so All right, so the summary of the atomic radius is that if you choose going from, if you're looking at the element from top to bottom, atomic radii will increase, right? The reason for that is because the number of principal quantum number increase. That's why the size increased, okay? And going from left to right, or you can memorize right to left, it doesn't matter which one. This one, if you go this way, you are going to not use the number of energy shell. You are going to use effective nuclear charge if they have the same number of energy level. And going from right to left, right, the effective nuclear charge would be lower. That means the outer shell electron will experience the nuclear charge less. Therefore, the size will get bigger, okay? Which is the opposite from what I mentioned earlier, right? So if you go the opposite like this, right? If you go from left to right, of course, effective nuclear charge would be on the opposite, right? Effective nuclear charge would be higher, right? So we already compared between sodium and phosphorus. Therefore, the size would be lower, smaller. So you can memorize one, okay? So just stick with one. Okay, whether it's going to be higher effective nuclear charge or lower effective nuclear charge. Okay, so it just, you can see in two different views here. All right, so if you're looking at the actual size, you probably notice that exactly what we mentioned, right? As the number of energy level increase, the size will also increase as well. As the effective nuclear charge decreased, you are also going to observe the size getting bigger as well. Okay. All right, so what I have not talked about yet is, so far the example that I give you are the main group element. What are the main group element? Well, we already discussed that in the previous video, okay? So main group element are those elements in the S block and the P block, right? For the D block, which are the transition metals, the trends are not very predictable. So that's why we separate them into two categories, right? Main group element would follow the trend very well, but the transition metal, there will be some deviation. Okay, so for example, in this case, for when we talk about main group, the transition metal, you will see that it's going to have some deviation right here. Okay, so that means in this case, it's not likely to be predictable. So that means on the exam, what you are going to observe is that most of the element I'm giving to you in terms of ranking atomic radius is going to come majority from the main group element, right? So for example, if you're looking at this graph, right, radius plus against atomic number, if you're looking at group 1, right, group 1, smallest would be lithium, and as you go down the column, you are going to see that the size would get bigger. It's exactly what we mentioned earlier, right? So same thing for group 8 as well, right? So the size would get bigger as you move from top to bottom, okay? So just note that this slide is just tell you that the transition element is not going to follow the trend. Next, we are going to take a look at the trend in electronegativity values. What is electronegativity? Electronegativity is the ability of an atom to attract electron to itself in a chemical reaction. Okay, so it's missing right here is the chemical reaction. Okay, so the value of electron negativity is quantified by Linus Pauling. So pretty much in his publication, he described the electronegativity value as the power of an atom in a molecule to attract electron to itself, right? So the higher ability to attract electron, you are going to get a higher value of electronegativity value. I'm going to use EN for short for electronegativity value, and let me say it again. The higher the value of the EN, it means that an atom will be able to attract electron to itself stronger. Okay, so that's what it means here. Okay, so let's take a look at the size of the atoms, and we are going to use the size of atoms to help us predict the electronegativity value. Okay, so what we are going to look at is we are going to look at the element on the periodic table, except we are going to ignore the last group, which is group 18 or group 8A, which is the noble gases. The reason for that is because the noble gases already have stable electron configuration, it doesn't want to attract or accept any more electron. Okay, so because already have stable electron configuration, therefore it doesn't want to, okay, so they do not want to attract any more electron. Okay, so that means in this case, what we are going to do is we are going to pretty much not consider group 8A or group 18, okay, because they are not going to form compounds. They're not going to attract electron, okay, so they're already stable. So what we're going to take a look at is we are going to take a look at the rest of the element, okay. What we are going to take a look at is, remember we talked about two things before, right? When we talk about the size, one is the number of energy level, right? So it's the number of shells, right? So one is the number of shells, energy shells, which is the N value, and the other one is the effective nuclear charge, right? Which is the number of proton minus shielding electron, right? In the previous slide that we talked about. So we are going to use those two ideas still to help us determine the size, and the size of the atom will also determine how an atom will be able to attract electron as well, which is going to determine the electronegativity values. Okay, so two things that I'm going to consider first would be the hydrogen and fluorine. Okay, so those are the two that I'm going to consider first. Okay, if I look at the atomic structure of hydrogen and also of fluorine, this would be atomic structure of hydrogen and fluorine. Okay, so hydrogen has a smaller size than fluorine, right? Clearly, it has only one energy level. Fluorine has two. Okay, so fluorine has a bigger size. Which one would have a stronger attraction then? Okay, so seem like, well, this one is closer to the nucleus, right? It should have a stronger attraction. This one is further away from the nucleus, should have weaker attraction. Is that true? Well, in this case, what you need to do is you need to use the effective nuclear charge to help us determine that, right? Ability of this atom to attract this electron. Ability of this atom right here to attract this electron or accept this electron into its layer, right? That's what it means. How can we do that? Okay, so we are going to use effective nuclear charge the same, right, to calculate for this. Effective nuclear charge for this electron that experience the hydrogen, the proton in the hydrogen would equal to +1, right, because it's 1 proton minus shielding, right, 0 equal to 1. If you do the same thing for fluorine, you are going to get 9 proton minus shielding. Remember, fluorine already contains 2 electrons inside the inner layer. The outer layer contains only 1, 2, 3, 4, 5, 6, 7. So it's not meet the octet yet, or it doesn't meet the 8 electron that is going to be the same as noble gas yet, right? Therefore, in this case, if one electron is accepting, it's going to be accepted into this layer. Okay, so again, if I would write electron configuration for this, for fluorine, right, it's going to be 1s2, 2s, 2, and then 2p5, right? Okay, so that means in this case, if you add number of electrons together in energy level 2, you have 2 plus 5, that's equal to 7, right? So that's why there are 7 electrons out here. Okay, so that means you probably notice that 2p subshell contain only 5 electrons. It has not filled yet. Therefore, if you want to add one more electron in, it's going to be added to this 2p, right? So that means it's going to be added to this level. Okay, so it's going to be added into this level. So therefore, in this case, if you consider this electron right here, how much it's going to experience atomic nuclear charge? It's going to be 9, right, from the proton minus the inner shell. Okay, so these are the inner shell, which is only 2. Therefore, in this case, this electron here is going to experience positive 7 of the nuclear charge. Okay, so as we mentioned earlier, the stronger effective nuclear charge, right, is going to means that it's going to experience a stronger effective force from the nucleus. Therefore, in this case, the electron is most likely to be withdrawn closer to the nucleus, right? Higher effective nuclear charge, higher ability to attract electron. Therefore, in this case, fluorine would have higher electronegativity than hydrogen. Okay, so even though hydrogen is smaller size. Okay, now if you're looking at the trend of these, it's pretty much going to fall into the same trend as the atomic size. Okay, so which means that you are going to look at, if you're looking at compare between this one, right? So the same row, if you're looking at this same row right here, okay, you are going to see that fluorine would have the highest effective nuclear charge. Therefore, fluorine would have the highest ability to withdraw electron to itself. If you're looking at top to bottom, so this group right here experience the same effective nuclear charge, but fluorine is smaller size, right, compared to like iodine or bromine. Therefore, the smaller size is easier to attract electron to itself, right? It's closer to the nucleus, so that means it's going to be easier to attract electron, more electron to itself. Therefore, in this case, the trend of the En value would go from bottom up, right? So it's going to increase from bottom to top, and it's going to increase when it gets closer to the fluorine. Therefore, I want you to note that the highest En value on this periodic table would be fluorine. And you are going to see as well, it's going to follow by nitrogen and oxygen. Okay. All right, the reason for that is because, again, if you compare between fluorine and chlorine, right? So fluorine would have 3 layers. So 1, 2, 3, right? Versus chlorine would contain 4 layer, 1, 2, 3, 4. Therefore, in order to attract one more electron, this is going to be easier than attract, this is further away of the electron, right? So therefore, in this case, fluorine would have higher En value than chlorine, bromine, or iodine. Okay, so it's because of that size right there. Okay, because they both have the same effective nuclear charge. All right, so now let's take a look at ranking here. So we are going to rank these in terms of decreasing electronegativity, which means that you are going from the highest, right? And you are going to find out the lowest of the element that have the lowest En value. Okay, so what we are going to take a look at is fluorine, right? According to the trend that we see earlier, would have the highest En value because have the highest effective nuclear charge, and it's also small as well compared to the rest of the element except hydrogen, right? And then it's going to follow by oxygen, and the lowest one would be rubidium because rubidium is the biggest, right? It's have the biggest size. It's have very low effective nuclear charge too. Therefore, it's going to have the lowest En value, and then it's going to follow by silicon and magnesium. Okay, so that means, again, when I ask you on the exam, I'm going to ask you to rank. You also need to be able to tell me about the reason as well. Okay, so the reason for the electronegativity is you are going to look at effective nuclear charge. Okay, and then you are going to look at size. Okay, which is the En value, right? The number of N, the number of electron shells, right? The effective nuclear charge will tell you about pretty much why it's going to, how it's going to attract electron and things like that, right? Because it's the attractive force from the nucleus. Okay, so if you look at the atomic radii versus electronegativity value, you will see that that will be the opposite, right? The bigger the size is going to have less attractive force to the nucleus. The En value would be lower. The smaller size would have a higher ability to attract electron. Therefore, the size and the En value would be the opposite. Next, we are going to take a look at the size of an ion. Okay, so what we are going to take a look at is we're going to compare between the neutral atom versus the ions. Okay, whether it's cation or anion, so we're going to take a look at those. Okay, so we are going to first look at the lithium and oxygen. Okay, so according to this, if you draw electron configuration, you are going to get one s2 2s1, right? So that would be for lithium. For oxygen would be 1s2, 2s2, and 2p4. Okay, so therefore we are going to use these in order to help us to draw the electron shell models. So these contain only 2 energy shells. These contain 2 energy shells as well, but the second shells contain different number of electrons. Okay, so I'm going to go ahead draw for lithium ions and also lithium neutral atom as well. This is lithium neutral atom where the nucleus contains 3 positive charge because lithium has 3 proton. Okay, so that's why there are 3 positive charge here. So the first layer contains 2 electrons, the second layer contains 1. Lithium plus indicate that it's going to, the outer shell valence electron going to be removed by 1 electron, right? So we are getting rid of this, therefore the size would get smaller because get rid of 1 layer. Okay. Now with oxygen, okay, so if you draw the neutral molecule of atom of oxygen, it's going to contain 6 electron total in the outer shells. Okay, when it accepts 2 electron, okay, so accept 2 more electron, this oxygen now become an ion with 2 negative charge. The size of the ionic radii would get bigger. The reason for that is because the size of the energy level are the same, the effective nuclear charge are the same, but what is increasing is the repulsion between electron and electron, right? Because you are cramping 2 more electrons in the same energy level, therefore in this case the electron repulsion would increase, therefore it needs to get a little bit further away from each other, therefore it's going to cause the size to increase. Okay, so that's what you are going to observe here. So if I summarize this, right, so if you are going from neutral atom to cation, the size will get smaller. The reason for that is because you are minimize repulsion, electron repulsion. And sometimes if that valence electron is the outer shell and you get rid of the whole shell, you are going to get a lot smaller because you actually get rid of the energy shell, right? Or sometimes it just means that you get rid of energy shell. Okay. However, if you are going from neutral atom to an ion, this is when you add electron into the atom, the size would get bigger. The reason for that is because you are going to adding the electron repulsion. So therefore in this case, the electron would stay further away from each other, therefore it's going to increase the size of the atomic radii. Okay, so again, the atomic radii is the radius that measure from the nucleus to the electron that left in the ions, right? So this would be the distance from the nucleus to wherever the electron is left in an atom or in an ion. Okay. So now let's take a look at example 4 and 5. Okay, so between rubidium and rubidium plus 1, which one would be larger? Of course, in this case, rubidium would be larger because you did not get rid of like one of the energy shells, right? So if you draw the picture of it. And between iodine and iodine minus would be bigger because you are increasing electron repulsion for that. Okay. Now, if you are going to rank between anions of nitrogen, fluorine, and phosphorus, what you are going to get is you are going to look at this first, right? So we have phosphorus. Okay, so I'm going to circle that. Okay, so phosphorus, we have nitrogen. Okay, we also have fluorine as well. Okay, so if you're looking at the size in general, you will notice that nitrogen would contain 2 energy level because n equal to 2. Fluorine would also contain n equal to 2 as well. Phosphorus equal to n equal to 3. Have 3 energy level for phosphorus, 2 energy level for nitrogen, and 2 energy level for fluorine. So therefore, in this case, if you add more electron, right, because you are going to make this to be accept more, 3 more electron, right? So add, okay, let me actually write the word add instead of positive, add 3 electron, okay? This one you're gonna add 3 electron also. This one you're gonna add only 1 electron, okay? So if you compare between nitrogen and fluorine, okay, so clearly for fluorine, without adding any electron, fluorine has smaller size than nitrogen because of effective nuclear charge, because of higher effective nuclear charge that the outer electron experience, okay? But if you're looking at nitrogen and fluorine, because nitrogen accepts 3 more, therefore the electron repulsion would increase a lot more than adding just 1 electron. Therefore, in this case, the nitrogen 3 minus would have a bigger size than the fluorine that add only 1 electron to it, okay? Phosphorus is clearly already have 3 shells, right? Adding more is going to increase the size. So therefore, in this case, the biggest to the smallest would go from phosphorus ions to nitrogen ions, and the smallest would be fluorine ions, okay? And if you look at the picture here, you will see that this is the comparison between cation versus anion in comparison to the neutral atom. Okay, so these are neutral atom that indicate in green, gray. Okay, so for cation, you will see that the size will become a lot smaller because you minimize the electron repulsions, and also sometimes you get rid of the energy shells as well. So that's why the size will get smaller. For anion, on the other hand, because you are adding more electron to it, it will increase electron repulsion. Therefore, electron want to get further away from each other. Therefore, it's going to expand the size of the energy, right? So therefore, the size of the radius would get bigger as you increasing the number of electrons.